Hello and welcome to this TIMSS data analysis training video. In this video, we'll talk about how to calculate standard errors and statistical significance with the TIMSS data. In this video, we will do an overview of statistical significance and significance testing. We will talk about how to calculate significance testing in large-scale assessments. We will talk about different types of samples and the consequences for significance testing, and also give you an example of some of the consequences of not using the right analysis procedure. When we talk about statistical significance, this tells us if a particular difference is relatively large in relationship to an error or uncertainty expected by chance. Depending on our interests, priorities, and consequences of the decisions that would be made, the threshold to consider something large or small will vary. We usually assume a normal distribution of the error. We then say that a difference is statistically significant when, based on a pre-established criteria, it is unlikely the observed difference is the result from samples taken from populations that are equal. Here we have a graphical representation of that. And what we're assuming here is that if A and B, two statistics, are computed from the sample that comes from the same population have the same parameters, then the average difference of those statistics will be 0. But it won't always be 0. Sometimes A will be greater than B, sometimes B will be greater than A. So there'll be some variability, but it gets to a point when there's a threshold that if the difference is larger than that, or in this case smaller or larger than this, then we say that it is unlikely that that difference would have been observed by chance, given that A and B come from two samples from the same population, and therefore we say this difference is statistically significant. So there are two things that are key here that are going to be key to the analysis of the data with large-scale assessments. One is, where does this arrow go? So what is the real difference? And the second, what is the distribution of that difference, or the estimated distribution of those differences? And it's where would you place these arrows to determine at what point the difference will be considered statistically significant. And that's what we do when we compute these standard errors, and that's why we'll see that the way in which standard errors are computed with large-scale assessment is not the same as when you compute them with simple random samples. So using sampling weights will help us locate the center arrow in the optimal location, and using replication methods will locate the other arrows in their optimal location. So we need to use both to get the proper statistical significance. There are two sources of error that we are concerned with in the analysis. One is the sample selection, and this is calculated using replications of the samples. And we do this by systematically changing the overall contribution from different units within the sample, recalculate the results, and summarize the difference between these replicates according to a formula. In the case of TIMSS, we use the jackknife 2 procedure, which was described in a separate video. When it comes to measurement, this is calculated using the plausible values. And here we compute the results with each plausible value and then calculate the variance of these estimates. In the end, we combine both portions of the error into a single statistic. It looks something like this, where we have the sampling variance and the measurement variance. It's important to mention here that the assumption here is that the samples come from a complex sample design, and there's also a complex assessment design, and that's why we have to implement these additional procedures to calculate these standard errors. The software and the programs that we will be showcasing during the academy will do the calculations taking these two errors into account. So whenever you see significance testing or standard errors computed, this is the way in which they're calculated. Another consideration when calculating significance, doing significance testing between two statistics, is the samples, the types of samples. So we have independent samples, and these are the ones where the units do not come from the same sampling frame, and therefore the errors are not correlated. This will be the case when we compare a country over the years, so between one year and the other, or when you compare different countries within the same year. The issue here is that when you have two independent sample selections, the errors between these two selections, the sampling errors between these two selections, are not correlated. This in contrast with dependent samples when the units or where the units come from the same sampling frame and the errors are correlated. Take the example of selecting schools from a sample, from a population, and having a sample that has boys and girls in it, and then you're comparing the average of boys versus the average of the girls. And since the boys and the girls were selected from the same school in this case, then the sampling error would be between both samples would be correlated. So anytime that you're comparing a variable within a country, the errors will be considered to be correlated, and also when comparing results from a country with an international or composite estimate. In this case, we need to take this dependency into account when computing the standard error of the difference. So between independent samples, we use the formula that we learned in Statistics 1, or the first course of statistics that we took, which is you combine the two variances of the two statistics and take the square root of that. And then we calculate the statistics with the corresponding error, use that formula for the error, and we get the t-test that ends up being the difference between the two statistics divided by the standard error of that difference. So this ends up being relatively simple. Again, this is for independent samples. When we're calculating the differences between dependent samples, then it gets more complicated. So here's the case of when we're not using plausible values. And notice that what we're doing here is we're actually computing this difference for each one of the replicates. In the case of TIMSS, 150 times. And then we're going to contrast this difference with the contrast of the full sample, square it, add them up, multiply by the F factor. When we are working with plausible values, then we have to add to this, we have to do it 5 times, once for each plausible value, and we have to compute the variance of the 5 differences that we obtain with each one of the 5 plausible values. So it does get more complicated. You will see that when we show you the IDB analyzer and the International Data Explorer, this is what they will be doing behind the scenes, which is why the analysis takes usually a long time. An alternative to using the formulas that I showed you just a few seconds ago is to use the regression approach to test differences between subgroups. And remember that in regression we have that we're testing the model whether the y is equal to a plus a regression coefficient times a variable. Now, if this variable takes on values of 1 and 0, then when this is 0, then that's going to give us the mean of the group that has 0 value here. And when x takes a value of 1, then the y is going to be the difference between a and a plus r. So r is going to be, in this case, is going to be the difference between two groups. So Using regression, in contrast coding the variables, or you can do any type of contrast coding of the variables. You can test for significant differences by using a statistical package that has regression as part of its tools, and that does jackknifing in the case of TIMSS. So you can use the TIMSS International Data Explorer or the IDB Analyzer to calculate errors of a difference. The IDB Analyzer automatically calculates differences between the subgroups whenever you compute means or percentages. But also careful coding of categorical and grouping variables in combination with regression statistics, you would also be able to obtain do significance testing of differences between subgroups or combinations of groups. Another scenario that you will face is computing the error of the difference with a composite statistic. An international average is a composite statistic computed as the average of several country means, or several country statistics. The error of the difference between a national statistic and the international composite one is as follows. So it is the standard error of that difference is the variance of the international estimate plus the standard error for that statistic for the country squared multiplied by this factor, number of countries minus 1 squared minus 1 divided by the number of countries squared. To then calculate the significance or the t-value, we divide the difference by this error here. So if we were to look at the difference between country A and an international average, we would compute the error this way and use this as the denominator to calculate the t-value. So often people ask, why does this matter? Does it matter to do it, which way we do it? And here I want to show you this table that has results from gender differences in TIMSS in 2015, and I believe this to be math. And so here we have the number of cases, the average achievement, and here we have the standard error calculated, taking into account the sample design and the assessment design. And you'll see that all these values are bigger than these values right here. And that's why I've made them red, because these are incorrect. These take into account the sample design. Same when it comes to the standard error for the girls. These are always a little bigger, sometimes a lot bigger than those calculated under the assumption of simple random sample. So the green ones is the correct way of calculating these standard errors. Here we have the standard error of the difference, and we'll see again that the errors calculated assuming simple random sample are not matching those calculated assuming or taking into account the sample and the assessment design. So the moral of the story is that you will, if you don't do it the right way, you will be using the wrong standard errors. The arrows in that distribution will be placed in the wrong location, and your conclusions and recommendations will be incorrect. Before finishing, I would like to show you another document that we distributed as part of the materials for the Academy, and it's in the additional materials folder, and it's called Calculating Standard Errors in Large-Scale Assessments. And if you open that document, you will find here that it has the parameters, and it has the different formulas that would be applied to calculate standard errors in large-scale assessment. The first set being for TIMSS in pearls which use the same procedures. Okay. The other document that you have there is one on using plausible values, and here I'm going to go in here, actually, what are plausible values and why are they useful. You open it up, and this will tell you the why plausible values are being used and why are they useful, and then it would also have some examples about what happens when you don't use the plausible values properly to estimate population parameters and their variance. To summarize what we covered in this video, we talked about some general principles about significance testing. We talked about when establishing statistical significance, it matters how we calculate the error. Our usual formulas for these calculations do not always apply, and by the usual formulas, I mean those that get computed by default with most statistical programs because they assume simple random selection of the cases. Using the sampling weights and the recommended replication procedures will give us the correct estimation of significance testing, and as a consequence, not calculating the errors correctly will then lead to the wrong result. So we encourage you to do the calculations in the right way, and by that we mean using the sample weights, using the replications of the samples, and using the 5 plausible values that are used for TIMSS. Thank you. We hope you enjoyed this video and learned something new. For questions about the contents of this video, please ask us by email by writing to egonzalez@ets.org or falk.brace@iahamburg.de, or ask us during our next online session.
This video was created for the academies held by the IEA ETS Research Institute. Any commercial use of this video is prohibited unless explicitly authorized in writing by the Institute or its funders. Funding for the Institute comes from the International Association for the Evaluation of Educational Achievement and the Educational Testing Service.